Okay. I'm going to pause here for any questions. Pause here for any questions. All right. Now, our third learning objective is to understand the mechanism of skeletal muscle contraction. And then we're going to also look at the mechanism of force generation in muscle. Okay, so the second and third objective is what we'll go on to look at now. Now, when we think about muscle contraction, we can think about a single unit of contraction, and that is called a twitch. So a twitch is like a single episode of a muscle contraction. The factors that affect the amount of force generated by individual fibers, we'll also talk about that. We'll talk about how we can regulate the amount of force, and then we'll talk about the velocity of shortening as well. Okay, so a twitch, we said, is a brief period of muscle contraction in response to a single action potential. It can be considered an all or nothing event. Just like we say with an action potential, it's going to happen in totality and then it's going to cease. And then another one will occur. So it's all or nothing. And then it can be identified on the basis of a single muscle fiber, on the basis of an entire motor unit. And remember, a motor unit is one muscle fiber and all, or one motor neuron, and all the muscle fibers it is innervating. Or we can think about a twitch on the basis of the entire muscle, okay? So we can think about a twitch of the biceps entirely, one motor unit of the biceps, or of a single muscle fiber within that biceps. Now, looking at the twitch, there are several phases or periods that occur that comprise a single twitch. So let's look at these different phases individually. First, it's the latent period. And the latent period is really a period of warming up of the muscle contraction elements. It's a time between the action potential up to when the muscle contraction actually begins. It's going to be a few milliseconds. And what explains the latent period is basically the time that it takes for the machinery to get warmed up, the time that it takes for excitation, contraction, coupling to get warmed up and to get started. All right. So basically, when we think about the action potential arriving on the motor end plate, the generation of the end plate potential, the spreading of that potential via the T-tubules out throughout the muscle, and then the DHP and ryanodine receptors passing that voltage change, that action potential, onto the SR, and then the SR releasing calcium, and then the calcium arriving on the troponin. So that takes time. All of the time that it takes, it's not a lot of time relatively, right? It's only a few milliseconds, but it still doesn't happen instantaneously. So between when the action potential arrives on the muscle and calcium arrives on that troponin, that is where we have the latent period. And notice, because the sarcomere hasn't begun shortening yet, there is zero force generation. So the tension, otherwise known as the force that is generated by a muscle contracting, that hasn't begun to rise yet because that requires the shortening of the sarcomere. And if troponin hasn't arrived onto, or sorry, calcium hasn't arrived onto troponin, then the sarcomere is not shortening, and then zero force is being generated. So notice that the latent period has zero force generation. The second phase is the contraction phase. And here we can begin to see the tension rise. This is where cross-bridge cycling has now begun. So now myosin and actin have connected, and there are cyclical, events of bringing actin closer and closer and closer to the M line. Now remember, actin isn't dragged to the M line immediately. right? This is a cyclical process. So myosin reaches up, drags actin, breaks that contact, makes a new point of contact, drags it some more, breaks that contact, makes a new point of contact, drags it some more. So that cross-bridge cycling will determine how much contraction is happening within the sarcomere, and that is a direct result, or that will directly determine how much force is generated. Okay, how much force is generated. The third phase of the twitch is the relaxation phase. And the relaxation phase is going to be the longest phase. It's longer than the contraction phase and definitely longer than the latent period. And this is where the muscle is going back to its original length. This is where calcium is being pumped back to the SR and it is leaving troponin. Those binding sites are getting covered up. The sarcomere is gradually relaxing back to its original length, its resting length. And then that is why this takes so much longer, because it's a more gradual process, right? More of a passive relaxation process, but also it's requiring time for the pumps to get that calcium back into the SR. Okay. So also, we want to make the connection here that the force generation tapers off. So as that sarcomere relaxes and goes back to its original length, then force generation tapers off because the sarcomere is no longer short. Okay. So just an illustration of that, I want to encourage you guys to practice drawing this out, practice drawing out what's happening in terms of the force generation and the curve, but also be connecting, be making connections to what that stands for with regards to either excitation and contraction coupling in the latent period or cross-bridge cycling in the contraction phase, and the calcium ATPase pumps, pumping calcium back into the SR responsible for the relaxation phase. And then I want to emphasize here as well that this entire process is a response to a single action potential. So that is what the basis of a twitch is. The events that occur in response to one single action potential. And again, this is all or nothing. So the latent period has to follow, the latent period has to be followed by the contraction phase and then the relaxation phase. Those three events must occur, and then we have another action potential bringing about the same events again. All right. Now we can think about two different types of twitches. And in order to do that, we have to think about some terminology. So first is the contractile elements. What are the contractile elements? These are the parts of the muscle that are actively moving or shortening. And this is going to be basically the sarcomere. The sarcomere is the only part of the muscle that is shortening, that is contractile. And it's really on the basis of those two contractile proteins, actin and myosin. The other things we want to think about are the series elastic elements. And this is basically the non-contractile components of muscle. So the outer connective tissue coverings like the perimysium, endomysium, epimysium, those are not contractile. They're only moving according to what's happening with the muscle. The tendons are also non-contractile. They're only anchoring the muscle to the bone. So the tendons are going to go from the muscle belly itself, the contractile part, to the bone, and it's only going to be dragged in one direction or the other, depending on what the actual contractile part of the muscle is doing. We also want to think about force exerted by the contracting muscle. That is referred to as tension. Okay, so basically when I lift an object, the force, which is the ability to do work or to move an object, that is going to be a result of how much tension is generated by shortening of the contraction. So in order for me to lift an object, my muscles have to shorten to the degree with which they generate enough force to move the object that I'm trying to move. So if this object is, let's say, 1 pound, then my muscles have to contract so that they can generate 1 pound worth of force or tension in order to move this 1 pound object. So that is what we mean by tension or force. And then the opposite to that would be the load. So the force that is opposing my contracting muscle is referred to the load. Another way to represent that is the weight of the object that I'm trying to move. Again, think about my 1 pound object that I'm trying to move. This is considered the load, okay? And so my muscles, again, have to generate enough force to oppose the weight of that load. Okay, now again, let's think about the 2 types of contractions here, isometric contractions versus isotonic contractions, and how they differ based upon the tension and the load. An isometric contraction is considered when the length of the muscle stays the same. And think about the word isometric. Iso means same, metric means the length. And so the length of the muscle doesn't change. Okay, the contractile elements will contract, but the muscle itself doesn't actually shorten. Here, the load is greater than the amount of tension being generated by the muscle. All right, what is creating the stretch is the series elastic elements. So here we can see you've got a muscle suspended across this apparatus here. It's being held just the way it would be in the body, suspended across 2 joints or 2 bones. And we have a force transducer, which is really mimicking a load, right? It's trying to lift some type of load. It's also going to be stimulated so that we can record how much electrical impulse or action potential, right? It's kind of mimicking the action potential, is being stimulated onto the muscle. And we're actually going to contract the muscle and determine whether or not it moves this load. All right, so here is the muscle contracted, and we can see that, right? It's bulged. So we know that some type of shortening is happening, but the load doesn't actually move. So the muscle doesn't actually shorten because the load is never actually lifted. So what's happening? The tendons are stretching. Notice the tendons here in the relaxed state are very short, and the tendons here in the contracted state have stretched out some. So in this type of contraction, we never overcome the load, okay, because the amount of force that we're generating is never enough to actually move or lift that load. All right, I'm going to take a brief pause here and see if we have any questions. Okay, so isometric, same length, the load is heavier than what the tension production is, and so we never actually overcome the load. If we look at the graphical representation of an isometric switch or an isometric contraction, we have the latent period, we have the period of force generation, and then we have the relaxation phase. Notice that we never have a flattening off of the curve. The curve goes up and then sharply comes down because there is never a period where we have enough load or have enough tension to overcome the load that we're trying to lift. This is an isometric type of contraction. Okay, and I want to go on to kind of bring this to real life. An isometric contraction happens usually at the beginning of an isotonic contraction. We're going to talk about what an isotonic contraction is coming up, but don't think of them as happening separately. An isometric contraction is happening when you're trying to lift a heavy object and it's not, and you don't lift that object right away, okay? There's a time where you're going to be trying to lift it, your muscles are going to be contracting, but you haven't generated enough tension to overcome the load just yet. So let's say you're trying to move a piece of furniture and it's just way too heavy for you to lift. So you're trying with all your might, your muscles are contracting, but the load is never being moved because you're not generating enough force to actually overcome that load. Okay, so that would be a real life example of when you'd see an isometric contraction. Let's talk about the isotonic types of contractions. This is where you have enough tension to move the load. Again, my 1 pound scenario, right? This is a fairly light object. My biceps can generate enough tension to move a 1 pound load fairly easily. And so with little to no effort, I can generate an isotonic contraction that immediately lifts or overcomes this 1 pound load. So let's look at our apparatus here and see what that looks like. So here's my muscle, again, suspended the way that it would be in the body. Here's the load that we're trying to overcome. Here's our force transducer. And then here's our simulator jolting this muscle to mimic an action potential. Now, because the muscle generates enough tension to move this load, the load actually moves, the muscle actually shortens. So this would not be isometric because the length changes. Automatically, we can disqualify this from being an isometric because the length changes and the load moves. If we look at the curve, notice that the tension flattens off after we have generated enough of that tension to move the load. It doesn't go up continuously because after we're generating enough tension, then we can flatten off the curve at that level. Okay. Also notice the degree of shortening. So the muscle is going to warm up to the latent period. Then it's going to shorten. Okay, here's the degree of shortening. And then it's going to eventually go back to relaxing. Okay, so an isotonic contraction is when you try to lift a load and your muscles can, in fact, generate enough tension to overcome that load, and the load actually moves, right? The muscle shortens, the length changes, and the load moves. Now let's look at a scenario here to compare what happens with isotonic and isometric contractions. So we start off with a 5-gram load. And if we think about our muscle in question, our muscle has the ability to lift up to 17 grams of weight, okay, up to 17 grams of weight. So if we try to lift a 5-gram load, that's fairly easy. So we're going to generate an isotonic contraction. There's going to be a period where the tension levels off. That's why we have isotonic, same tension. When we have generated enough to move the load, we don't have to generate any more. So the curve flattens off, the amount of tension flattens off at 5 grams, and we can easily move this load, and then the contraction ceases. Let's say we try to lift a 10-gram load with a muscle that can generate 17 grams worth of tension. Now, again, we're going to generate that load. It's going to take a little bit more time to get us warmed up here. It's going to be a longer latent period. We're going to generate that force. It's going to take us a little bit more force this time because the load is heavier. And then when we get to 10 grams, we're going to flatten off, and then we're going to go into relaxation again. Same thing is true for 15 grams. It's going to take a little bit more time, the latent period, to warm up because we have to generate more force. So that's going to require more calcium being released and more of the cross-bridge cycles happening. And when we get to 15 grams, it's going to flatten off. And then we're going to lift that 15-gram load. We're going to move the muscle. So there's shortening happening. And then we're going to go into relaxation. Now, because this muscle can only lift 17 grams, and now in this fourth situation here, we're trying to lift 20 grams. That's not feasible. So we're going to have a latent period that tries to warm up, tries to generate enough force, never actually generates enough force to sustain a 20-gram load, and then it's going to eventually just flatten, not flatten off, but level off. Okay, this would be considered an isometric contraction. The length of the muscle never actually shortens. The load is never actually lifted because feasibly, this muscle can only generate 17 grams of force, and it would never be able to lift or move a 20-gram load. So notice how isotonic contractions lift the load, isometric contractions try to lift the load, never actually get there. They still contract, but they never actually get there, and then they eventually level off. Okay, now in terms of our actual body and our muscle contractions, we can have some purely isometric contractions. So that is to say that we can try to lift the load, never actually lift it. So there can be a purely isometric contraction. Again, our real life example for that would be trying to lift a piece of furniture in your house, maybe a TV or a fridge or something, and you really cannot lift that. It's not feasible for you to lift that on your own. So that would be a purely isometric contraction. But purely isotonic contractions are very, very rare. Usually when you try to lift the load, even if you have enough force to generate that load, there's going to be a brief period of warming up. There's going to be a brief period where the contractions are isometric, and then you have an isotonic contraction where you actually lift or overcome that load. So that is to say that isotonic contractions are usually preceded by isometric contractions, and then they become isotonic. But isometric contractions can occur on their own. All right. Now, we also want to think, again, practically in our body, the load is not usually constant. The way that the load is appreciated is usually changing depending on our limb position, depending on our body position, depending on our body status. A really good example of this is, let's say you're carrying groceries, right? I'm sure we've all been in a situation where we're carrying just way too many groceries, trying not to have to make that second trip. And if you're carrying those groceries by your side, your body, your biceps would perceive that load in a different way than, let's say, you were carrying the groceries close to your body or carrying the groceries over your shoulder. So your body position changing will definitely change the way that your muscles are perceiving that load.